In this video, we're going to take a look at extending the binomial expansion. So in the first year of study, we learned how to use the binomial expansion where n is a natural number. In other words, where n is a positive integer. What we're going to do now in this video is extend the binomial expansion, n being a fraction or a negative number. So what we're going to do now is just state the result here that we need for when n is now a fraction or a negative number. And this result is given in the formula book, so you don't have to worry about memorizing this result. So let's say we've got something of the form 1 plus x to the power of m. And like we said here, n now is either a fraction or a negative number. And the result that we're going to use here is 1 plus n times x, so nx. We then have n times n minus 1. This is all over 2 factorial, and we times this here by x squared. We then have n times n minus 1 times n minus 2. This is all over 3 factorial, and we times this now by x cubed. And you can clearly see the pattern that's forming here. So this would keep going on and on. But like you can see, the pattern's quite clear, I think. So n times n minus 1, it would be over 2 factorial times x squared. N times n minus 1 times n minus 2 over 3 factorial times that by x cubed, so on and so on. Okay. So this is now for when n is a real number. So where n belongs to the reals. Okay. So one important point to make here is for the first year of study for the binomial expansion, the series that we worked with were all finite series because n was a natural number, whereas now, because n is just a real number, the series now are infinite series. Okay, so that's an important point to be aware of here for when I'm working with the binomial expansion when n is either a fraction or a negative number. And we also need to be aware that the expansion here is valid when x is between minus 1 and 1. So we have this condition here for validity. So this is valid when, so like I said, this is valid now when x is between minus 1 and 1. So the main way that you'll see this presented here, usually in textbooks, for example, is mod x is strictly less than 1. But this just means the same then as x being between minus 1 and 1. Okay. So what about if we're expanding something of the form 1 plus bx to the power of n? How does that affect the validity now? So 1 plus bx to the power of n. Well, this would be valid when mod bx, so mod bx here is strictly less than 1. We can rearrange this now, so we then have mod x is strictly less than 1 over b. And then if you find this alternative notation here a little bit easier, then this would mean x is between minus 1 over b and 1 over b. So minus 1 over b and 1 over b. Okay, so that's the alternative there. And then finally, what about if we're working with something, say, like a plus bx to the power of m? So a plus bx to the power of m. So for these two examples here, we can go straight into using this result here. Okay. The reason for that is because it's of the form 1 plus x here to the power of m. So this 1 here means we can just use the expansion or the result here for the expansion straight away. Whereas now, if we have something, say, a plus bx to the power of n, so this number here is anything but 1, then we can't use this result straight away. Okay. So what I need to do in this case then is factor out a to the power of m. So this would be of the form then, a to the power of m times by 1 plus b over a x, and that's all to the power of n there. Okay. And again, how would this now affect the condition here for validity for this expansion? So this would be valid when So valid when So in this case now, this is now mod b over a. So b over a x being strictly less than 1. Again, we can rearrange this then. So what we're going to get here then is mod x is strictly less than a over b. And again, if you prefer this alternative notation here, then what we're saying is x is between minus a over b and a over b. So minus a over b and a over b there. Okay. And there we have it. So that's everything that we need there for our introduction here to extending the binomial expansion. There's not too much detail really to this. The main things to take away here is this result. Like I said, this is given in the formula book, so you don't have to worry about memorizing this. And then also being able to kind of show for when these series are valid for. So you will get asked this quite a bit on typical kind of A-level maths binomial expansion questions. So make sure it is something that you are comfortable doing. Okay, so that's everything that we need there then for our introduction. So what we're going to do now is just take a look at some practice questions here for extending the binomial expansion. Starting off with question 1 here then, we want to find in ascending powers of x the binomial expansion of 1 over 1 plus 2x to the power of 3 up to and including the term in x cubed. So where do we begin here? Well, the first thing I'm going to do here is rewrite this fraction using the rules of indices. So what I've actually got here then is 1 plus 2x all to the power of minus 3. Okay. So we don't need to use the result here that we saw on the previous page. And don't forget that result is given in the formula book. So that is 1 plus x to the power of m. So 1 plus x to the power of m. So this is 1 plus nx. We then got n times m minus 1. That's all over 2 factorial. And we times it by x squared. And if we're going up to the term in x cubed here, we've then got n times m minus 1 times m minus 2. That's all going to be over 3 factorial. And then we times that by x cubed. Okay. So in this case here then, n is minus 3. And the x that we use here is actually 2x. So the argument here changes for x, so it's now 2x. Okay. So in that case then, expanding 1 plus 2x, the power of minus 3. Well, this will be 1. We then got n times x, that's going to be minus 3 times 2x. So minus 3 times 2x. We've then got n times m minus 1. So n here is minus 3, so I've got minus 3 times minus 4. And that is all over 2 factorial, so that's going to be 2 times 1, giving us 2 there. And then we times this here by x squared. That's going to be 2x all squared. So 2x all squared. I'm just using a dot here just to kind of break up a little bit. So rather than using a multiplication sign, using a dot here, it still represents multiplication, but just so I don't have a cross here with the x's as well. I think it just makes the notation a little bit neater. And then we've got n times m minus 1 times m minus 2. That's going to be minus 3 times minus 4 times minus 5. So plus minus 3 times minus 4 times minus 5. This is all over now. So this is 3 factorial. So that's 3 times 2 times 1. That would be 6. And then we times that by x cubed. So that would be 2x all cubed. Again, just using a dot here to represent multiplication. So 2x all cubed. Okay. And all I want to do now is just simplify each term here as I go. So we can't do anything with 1. Minus 3 times 2x, that would be minus 6x there. Nice and easy. Minus 3 times minus 4, so that would be positive 12. We then divide that by 2. So that gives me 6. Then we times that by 2x all squared. So that would be 4x squared. So I've got 6 times 4x squared. So that would be 24x squared there. So plus 24x squared. And then finally here, I've got minus 3 times minus 4. So that's positive 12. We then times that by minus 5, so that's minus 60. And then we divide that by 6. So that would be minus 10. So let's do it over here just so I can keep notes. So I've got minus 10. We then times that by 2x all cubed. So that's 8x cubed. Like so. So that would give me minus 80x cubed there. So minus 80x cubed. Okay. And there we have it. So that's the binomial expansion there, up to and including the term in x cubed. Now the question doesn't ask for it, but if it was asking for the values here for what this expansion is valid for, okay, that would be mod 2x being strictly less than 1. So in that case, then mod x would be strictly less than a half. And in other words, then x is going to be between minus a half and positive a half. Okay, doesn't actually ask for it on this question, but it does usually ask for the values of x for which this expansion is valid. And in that case, that would be your solution there. Okay, so valid for. Like I said, it doesn't actually ask for it, but just so you can see what that would look like. Okay, and there we have it. So that's the solution there to question 1. Moving on to the final question now and starting with part A, we want to find in ascending powers of x the binomial expansion of the square root of 1 minus x up to and including the term in x cubed. So for part A then, where do we begin here? Well, I'm going to rewrite this square root here. So the square root of 1 minus x here, we can rewrite that as 1 minus x to the power of a half. So now we need to expand this here up to and including the term in x cubed. So let's write this down here. So 1 minus x power of a half. So we're using the result that we used in the previous question and the result that we introduced at the beginning of this video. I'm not going to write it down again here just to save a little bit of time, but that result is also in the formula book as well if you do need it. So what we're going to get here is 1. We then have n times x, that's going to be a half, times minus x here, so just be careful of that. So because it's 1 minus x here, our x actually minus x, like so. We then have n times n minus 1, so that's going to be a half, times by minus a half. We then divide this here by 2 factorial, so that's 2 times 1, giving us 2. Then we times this here by minus x all squared. Okay, so minus x all squared. Minus x all squared there. And then for the term in x cubed here, we're going to get a half times minus a half. And subtracting 1 from this here, we get minus 3 over 2. Okay. So what I've got there is n times n minus 1 times n minus 2. This here then is all over 3 factorial, so that's 3 times 2 times 1. So that would be 6. And then we times this here by minus x all cubed. Like so. So that's everything that we need there now. All I need to do now is simplify term by term. Well, I can't do anything with the 1, so we'll leave that as it is. A half times minus x, that'd be minus a half x there. So minus a half x. I've then got a half times minus a half, so that'd be minus a quarter. We then divide that by 2, so that's the same as times by a half, so that would be minus 1 over 8, and then we times that here by x squared. That would be minus 1 over 8 x squared. And then finally here, I've got a half times minus a half, so that's minus a quarter. We then times that by minus 3 over 2, and just be very careful with the signs here. So this is now going to become positive. So I'm going to get 3 over 8 here. Okay, so 2 times 2 times 2 is 8. So my denominator is 8. 1 times minus 1 times by minus 3, that becomes positive 3. I get 3 over 8 there, and then divide that by 6. So if we're dividing by 6, that's the same as times by 1 over 6. So that will simplify to be positive 1 over 16. But then we times this here by minus x cubed. Okay, so this would here, when we cube this result, this would actually be negative. Okay, so minus x times minus x times minus x is minus x cubed there. Okay, so altogether then, I've got minus 1 over 16 x cubed. Okay, and there we have it. So that's our expansion there for part A complete. So that's part A done. Moving on to part B now. It says by using a suitable substitution in your expansion in part A, obtain an estimate for the square root of 0.96. So how do we answer part B here? Well, this actually goes back to binomial estimation that we learned about in the first year of study. So now, if I consider this for a moment, so I've got the square root of 0.96 and our expansion here was for the square root of 1 minus x. So what I'm going to do here is just imagine the square root isn't there for a moment, okay, because they're both under a square root. So in other words, what I'm saying here then is, if I do it up here, part B, 1 minus x is equal to 0.96. And what this will do here is this will give me the suitable substitution. Okay, so solving for x here, then I can clearly see that x will be equal to 1 minus 0.96, and that would be 0.04 there. Okay, so my substitution here is x equals 0.04. So let x equal 0.04. So if x equal to 0.04, what I get then is the square root of 1 minus 0.04. And notice here now this would give me the square root of 0.96 like we're looking to estimate for here. And that's going to be equal then, or this will be approximately, I should say, because this is an estimate. This would be approximately. So now we substitute this into our expansion here. Okay, so we've got 1 minus a half x, so minus half times 0.04. We've then got minus, so now I've got 1 over 8 times 0.04 squared. So 1 over 8 times 0.04 squared there. And then finally here, minus now 1 over 16 times 0.04 cubed. Okay, that's everything that we need here then. So what I can see now is the square root of 0.96 will be approximately all of this evaluated. So all you need to do now is just put this into your calculator here. I won't give each number because obviously this keeps getting smaller and smaller as we go along here. But if you do this correctly, what you should get then is 0.979, so 979, and then we get 796. Okay, and that's all the digits there on my calculator. So that's what you should hopefully get here for the square root of 0.96, or the estimate for the square root of 0.96. So that's part B done. Then for part C here, it says hence or otherwise obtain an estimate for the square root of 6. So how do we do part C then? Well, we're going to run out of room here to have a go at part C. So if you haven't already, do take a note of all this here. I'm just going to quickly clear the screen so we can attempt part C. So what we do need here then for part C is that last line of working. So the square root of 0.96, we said that that was approximately 0.979, so 0.979796 there. Okay, so how can we use this here to obtain an estimate for the square root of 6? Well, it comes down to this square root here. Okay, so the square root of 0.96. Well, I can rewrite 0.96 as 96 over 100. So what I've got here then is the square root of 96 over 100. And we're saying that this is approximately 0.979796. Well, using the rules of surds here, this would be the square root of 96 over 10. That would be approximately 0.979796. So from here then, what I'm going to do is I'm going to times both sides by 10. So I'm saying the square root of 96 is approximately 0.979796 times by 10. I'm not going to perform any calculations as I go here. I'll do those at the very end. But the square root of 96, we can actually simplify that. So the square root of 96 here. So that is equal to the square root of 16 times by the square root of 6. Square root of 16, obviously we know that's 4. So what I get here then is 4 root 6. Okay. So obviously if I just want an estimate for root 6, I'm just going to divide both sides here then by 4. So do it up here. So the square root of 96, like we said, that's 4 root 6. So I get 4 root 6 is approximately 0.979796 times by 10. And then finally, we want an estimate here for root 6. I'm going to divide both sides by 4. So therefore, root 6 here will be approximately 0.979796 times by 10. And then we divide all of this here by 4. Okay. And you put all of this into your calculator here to give us an estimate for the square root of 6. What I get here on my calculator is 2.44949. Okay. And there we have it. So I give an estimate there for the square root of 6. You can give this a quick sense check here. So if you put the square root of 6 into your calculator, so if I quickly do that on mine, what you'll see is you get something very, very close to this. So the square root of 6 on my calculator here, I get 2.449489743. And you can see then that this is pretty accurate. So that would be what, 5 decimal places. So yeah, we're happy with that. Seems sensible. And there we have it. So that gives the solution there to the very last question. And that brings the end of this video on extending the binomial expansion.